Welcome back to ECE 442-542. This is part C of lecture 5.3 dealing with Ragazzini controller design strategy. And what I want to do in this segment or this part of lecture 5.3 is actually work through an example. The example we're going to start with is this particular plant, G of Z. It's second order, it has two poles, it has 1, 0, and you can start to see some of the issues that might be arising when we're going through these restrictions on the Ragazzini design approach. You can hopefully see by the factored nature of this particular transfer function that we actually have a pole outside the unit circle at 2, and we also have a 0 outside the unit circle at 1.5. How many, or what is our pole 0 excess, or how many zeros do we have at infinity? We have a pole 0 excess of 1. So that's going to be important also as we work through this Ragazzini approach. Here are the observations then with respect to G of Z. Oh, I'm answering our own questions, aren't I? A little ahead of the game. G of Z has a pole 0 excess of 1. We have two poles, one finite 0. That gives us a pole 0 excess of 1. We're defining the pole 0 excess to be with respect to finite poles and finite zeros. So here we have two finite poles and one finite 0. Our pole 0 excess is 1. From restriction 1 on the Ragazzini design approach, that says then that our desired closed loop transfer function, which is what T sub C of Z represents, that must have a pole 0 excess of at least 1. That's restriction 1. We need T sub C of Z's numerator polynomial to be a degree less than, at least a degree less than, the degree of the denominator polynomial in T sub C of Z. G sub C, or G of Z, has an unstable 0, and that 0, as we said before, was at 1.5. That means from restriction 2 that we need our desired closed loop transfer function to obtain a numerator that possesses a 0 at that location. So now we need a polynomial in the numerator. It's going to now factor, and one of the factors in that numerator needs to be a factor that has a root at z equal to 1.5. We don't yet know how big alpha of z is going to be in terms of a polynomial. Maybe I should put that in square brackets. And now our denominator polynomial, we have not yet decided what that's going to be. Let's just keep it at the generic definition of denominator of T sub C of Z. That's our desired denominator polynomial. And in this example, we were given no design or performance specs, other than we probably want to stabilize the system. This system in the open loop is unstable. I don't think we want to live with that. But we were not given any percent overshoot, settling time, or peak time specifications. G of Z has an unstable pole at z equal to 2. That means that we want this expression, 1 minus T sub C of Z, evaluated at that pole. We want the 0, or we want a 0 factor in 1 minus T sub C of Z to be such that it vanishes at z equal to 2. So we want that 1 minus T sub C of Z evaluated at z equal to 2 to equal 0. So now let's see what that means relative to designing this T sub C of Z. Remember, this is our desired closed loop transfer function. And we already know that n sub t sub c of z has a particular piece to it. We haven't yet filled out the pieces, and we haven't yet decided what we want our closed loop poles to be for our desired closed loop transfer function. So restriction 2 says that we need t sub c of z to retain the unstable zero factor from g of z, or that says that we now have this alpha of z, that's yet to be determined, times this factor z minus 1.5. That's the factor that needs to be retained. This factor still needs to be determined. Now, since we were not told, or we were not given any performance specifications or design specs, no settling time, no percent overshoot, no peak time, suppose we just place the poles of t sub c of z at the origin. That's an okay location in the z-plane, and in fact, that's referred to by the phrase deadbeat response. If we want all of the poles of our desired closed loop transfer function to be at the origin, to be at z equal to 0, that means that we're asking for a deadbeat response, or all of the closed loop poles of t sub c of z are at z equal to 0, or they are at the origin in the z-plane. Restriction 3, again, restriction 2 and restriction 3 combined are trying to avoid, are forcing us to avoid not canceling unstable poles and zeros with our controller capital C of z. So now that g of z has an unstable pole at z equal to 2, that means that we need 1 minus t sub c of z evaluated at the unstable pole location. We need that to be 0 so that we ensure that there's a zero factor in the expression for 1 minus t sub c of z. If that's the case, let's go ahead, and we know the numerator has this piece to it, and we know that our denominator we said was going to be deadbeat. Let's just keep it at all of those poles in t sub c of z being at the origin. And in this case, let's try k. So now that is, we're letting that more general polynomial alpha sub c just be a constant k. Notice that t sub c of z has the correct pole zero excess. We needed t sub c of z to have a pole zero excess of 1. And we've accomplished that by simply allowing t alpha of z to be a constant. If it was something bigger, if alpha of z was now k, z minus, I don't know, let's say 1/4, then we would have had to increase the order of our denominator to make it a cubic in order to preserve the correct pole zero excess of 1. We have this unstable pole in g of z. Now we've tried to, we're saying let's try alpha z equal to k, and let's see if that gives us enough. Right now we only have one yet to be determined constant in this entire expression for our desired closed loop transfer function. Will that be enough to allow us to satisfy restriction 3? We know the location of the unstable pole is at z equal to 2. Restriction 3 says that 1 minus t sub c of z evaluated at that unstable pole location better be 0. Or 1 minus t sub c, we're evaluating t sub c at z equal to 2. That's 1 minus, and we know the structure of t sub c. That was k times z minus 1.5. Z we're replacing with 2. And we had a z squared downstairs, but we're replacing z with 2, or we're evaluating t sub c of z at z equal to 2. And we want to set that equal to 0, and that's looking like we can solve that for k. Whether or not we'll be happy with what we end up with is another story, but now we have one equation in the one unknown k. If we look at this, then we have k times 1/2 over 4, and that's equal to 1. Or, if we solve that for k, k is now equal to 1/2. Or you can see that different ways. You can say, oh, k over 8 is equal to 1. Well, then k must be 8. Now we've found everything that was yet to be determined in t sub c of z. T sub c of z, which is our desired closed loop transfer function, is now k, which we found to be 8, z minus 1.5 over z squared. That's now our t sub c of z. And you might ask, on a practical note, let's do an aside, is that desired closed loop transfer function, t sub c of z, is that even okay? Well, you might say, what is the DC gain of t sub c of z? How do we find the DC gain of t sub c of z? I'm looking for hands and I'm not seeing any, but oh, that's because I'm in an empty room. Sorry about that. But you can hopefully be continuing with this. What is the DC gain of t sub c of z? We want to know, what does t sub c of z equal when we replace z with z equal to 1, or at a DC frequency? This now says that we have 8, 1 minus 1.5 over 1 squared. Or that's now 8 times minus 1/2, or that's equal to minus 4. That's our DC gain. What does that mean? Well, that means that this is our closed loop transfer function's DC gain. The system is stable. All of the poles of our desired closed loop transfer function are inside the unit circle. They're at z equal to 0, so we have a stable closed loop system. It will stabilize if we inject a reference input to that closed loop system. Let's say we put in a value of 1. What will the output be? The steady state output, after the transients have disappeared, it's going to go to 1 times the DC gain. It's going to go to minus 4. Is that acceptable? Probably not. But remember what we started with. However, the original plant, G of Z, was actually unstable. At least now we've stabilized the system, and we've made it pretty fast. It's deadbeat, which means that we're beating the response dead in a finite number of steps. In fact, we have 2 steps to go to reach deadbeat, since it's a second order transfer function. So in 2 steps, we're going to be at a steady state, which is better than going unstable, which is what we had in the original plant. But now we inject a 1 and we go in the opposite direction and we end up at minus 4. But at least we're stable. We're staying at minus 4. Let's go ahead and finish up the design just to illustrate the controller design process. But so that's the end of the aside. But the aside was essentially, now that you've said alpha of z is a constant k, this is what we ended up with. And, well, maybe it's okay. Maybe not. But let's just see what the controller looks like. So here's step 2 of our 2-step controller design process associated with the Ragazzini approach. We have 1 over g of z. We know g of z. We now know capital T sub c of z. So we can plug all of that in. We have the inverse of the plant, and we have this ratio of our desired closed loop transfer function. What we can see is that this factor cancels, so that possibility of having our controller trying to cancel that unstable 0 has now been removed. That's the purpose of restriction 2. Well, we kind of have a mess here, don't we? So let's clean that up. We now have, let's put this over a common denominator. We have z squared minus 8z minus a minus 8 times 1.5, or plus 12. So 8 plus 4, and that's over z squared. Well, this z squared cancels that z squared, and this 4 can cancel some of that 8, half of the 8. So let's clean this up a little bit. We have 2 in the numerator. This can also go upstairs since it's in the denominator of the denominator, or we now have 2 times z minus 1/2 z minus 2. That doesn't look good because well, let's see. We had an open loop unstable pole at 2, and that's going to cancel it unless we've now canceled that effect, which we have done by restriction 3. We now have downstairs, we have z squared minus 8z plus 12, and that actually can be factored as z minus 6 and a z minus 2. And that's what we wanted. Now we've eliminated the possibility of that unstable pole being canceled, and our controller now is 2 z minus 1/2 over z minus 6. We now have a first order controller. What can you tell me about this? Well, if we look at that, this controller is actually unstable, but it's not canceling an unstable 0. We had an unstable 0 at 1.5. That's not being canceled. We had an unstable pole at 2. That's not being canceled by anything in the numerator. So this C of Z is good in that there's no unstable pole or unstable 0 cancellations occurring between this controller C of Z and the original plant G of Z. That's what we want to prevent. We want to prevent our controller from canceling anything outside the unit circle. You're seeing, though, that we had an unstable plant. We apply an unstable controller. This is where sort of two wrongs make a right. Now we have two unstable subsystems. We combine them in this unity output feedback configuration, and wow, we have a stable closed loop system. That's what's happening here. We have an unstable controller combined with an unstable plant, and it's actually producing, this is by design, yielding 8 times z minus 1.5 over z squared. That's how we designed C. Again, maybe that's not the best performing closed loop transfer function, but at least it stabilizes the system in the closed loop. Let's now look at its time response behavior. We really know where it's going to settle, but let's go ahead and work through that. Now we have T sub c is y over r. We know that by design is 8 times z minus 1/2 over z squared. Well, in order to put that into a difference equation, let's make this ratio of polynomials be in terms of powers of z to the minus 1. Then we have delays. That's maybe a little cleaner to look at. Let's then multiply that by 1. And in so doing, we get a colorful answer. If you turned away, you missed that, but my hands are getting a little bit heavy apparently. But now if you distribute this around, this numerator is 8z minus 12. We distribute that z to the minus 2 through both terms, and we have 8z to the minus 1 minus 12z to the minus 2, and we have a 1 in the denominator. We do a cross multiplication, and we see y of z is equal to r of z scaled by 8z to the minus 1 minus 12z to the minus 2. Now, let's do the really hard analysis. That's the frequency domain relationship between our reference input and our output y. What does that look like in the time domain? That now gives us 8 r of n minus 1 minus 12 r of n minus 2. Remember, z to the minus 1 corresponds to a delay of 1. The inverse z transform of capital Y of z is just y of n. The inverse Laplace transform, the inverse z transform of r of z, I hope I said that right for y. The inverse z transform of y of z is y of n. The inverse z transform of capital R of z would just be r of n, but we have some delay operators in there. And now what do we see? We see that there's a 1 time step delay between the input, r, and when we see it in the output. That actually is associated with this pole zero excess of 1. We have a 1 sample period delay between the input and the output, and we're seeing that in this difference equation. So recall, T sub c of z had a pole zero excess of 1. So, well, that means we have a 1 sample period delay between the input, which in this case is r of n, and the output, which is y of n. So if we wiggled the input, we're not going to see that wiggle immediately at the output. We have to wait 1 time step. So we wiggle the input, 1 time step later, we see that wiggling at the output. Let's now just walk through that. Since we have the difference equation in the time domain, let's go ahead and just put some numbers in. We can iterate on what the different values of the output are going to be. Suppose we let r be a unit step, or r of n is equal to 1 for all n greater than or equal to 0. What's y of 0? Well, y of 0 is 8 times r of 0 minus 1, or r of minus 1, minus 12 r of n 0 minus 2. R of minus 1 is 0, r of minus 2 is 0. We have 0 minus 0, or y at times 0 is 0. We wiggle the input at n equal to 0, and y of 0 doesn't instantly change. Again, we had that 1 step delay because of our pole zero excess of 1. What about y of 1? Well, we would expect it to respond since there's just a 1 sample period delay. This is now 8 r of 0 minus 12 r of 1 minus 2 or minus 1. Now we have 8 times 1 minus 12 times 0, or now we hit the system with a 1 time step later, wow, the output booms up to 8. What happens at y at 2? Now we have 8 r of 1 minus 12 r of 0. Or this is now 8 minus 12 or minus 4. What about y of 3? Difference equation hasn't changed. It's just the arguments of these r's. This is now n minus 1. N was 3, so this is 8r of 2 minus 12r of 1. Again, this is 8 times 1 minus 12 times 1 or minus 4. And as we said, after 2 sample periods, we've now locked on to our steady state value. We had to wait 1 sample period. We stayed at 0 in y of 0. Then at time 1, we shot up to 8. Then at time 2, we went down to minus 4, and now we're just going to stay there at minus 4. And we knew that already based on examination of our closed loop transfer function, capital T sub c of z. Acceptable? Well, remember, our open loop system g of z was unstable, and now we've stabilized it. So it's probably not the best behavior. We started with, or we input an r of n equal to 1, and we end up with y steady state being minus 4. So we've gone exactly in the opposite direction, but we have stabilized the system. And maybe I should say the closed loop system is stable. What you're going to see then is the Ragazzini design is not the best. That's not the best controller design, but it does get us thinking about the right questions. And what are those right questions? Well, is our controller that we design causal? It has to be causal. We can't have an output of our controller before we even excite the controller. We also know now that whatever design strategy we start looking at, we better not be canceling unstable poles or unstable zeros in our original open loop system with the controller. We also might be interested in steady state accuracy. Here, maybe that's not the best. We put in a 1, we go to minus 4, our steady state error is 5. We do want to know about our closed loop system. Here we haven't talked about the performance specs of T-settle, percent overshoot, or peak time. But what you're going to find, as in any control problem, there's always going to be a trade-off between steady state accuracy and transient behavior or performance. And that might be then, how does your system respond to excitations? How does it settle? What's the percent overshoot? How quickly does it get to its final value or its peak time? So we're always going to be worrying about this trade-off between steady state accuracy and transient behavior. We want to make sure our controllers are not canceling anything outside the unit circle, and obviously our controller needs to be causal. That's what we start getting in our heads by looking at this Ragazzini design, and we'll look at that a little bit more closely in terms of these restrictions, where they're coming from, and maybe another example. But that's now, you now know how to design controllers for discrete time systems.